Classical mechanics governs how physical bodies react to external agencies, everything from a still concrete pillar to the violent impact of a steel wrecking ball. Physics splits into two domains: quantum mechanics for microscopic atoms and classical mechanics for macroscopic objects. The classical branch divides into statics for bodies at rest and dynamics for bodies in motion. Dynamics subdivides into kinematics, ignoring forces, and kinetics, explicitly calculating them. For engineering mechanics, we make a critical assumption. We assume every object is a perfectly rigid body. This means we treat the object as if it never deforms, stretches, or compresses under load. If you are studying how a body internally deforms, you have crossed over into the strength of materials. Accepting the rigid body assumption is the necessary first step in engineering statics. By ignoring internal deformation, engineers can solve complex structural constraints purely through simplified vector mathematics. The base unit of statics is a single force vector. A force is simply an external agency that attempts to change an object's state of rest or uniform motion. You will encounter two primary units of force in your calculations. The Newton is the force required to accelerate 1 kilogram of mass by 1 meter per second squared. The kilogram force, or kgf, is the force required to move that same kilogram against standard Earth gravity. 1 kgf equals exactly 9.81 newtons. A force vector has four parameters: magnitude for size, direction for angle, point of application, and sense indicating a push or pull. These establish the principle of transmissibility. You can slide the vector along its line of action without changing its net external effect. There is a strict caveat here. Transmissibility is completely invalid for deformable bodies. If you move a push to the opposite side of a beam so that it becomes a pull, you have changed the internal stress from compression to tension. But within the rigid body assumption, the principle of transmissibility is a mathematical tool. It allows engineers to slide vectors around a schematic, aligning them at intersections to set up easier trigonometric equations. This 3D coordinate plane categorizes multiple forces. If all forces exist on a flat 2D grid, the system is coplanar. If they interact along the z-axis, it's non-coplanar. In a coplanar system, if every vector's line of action perfectly intersects at one point, it is concurrent. Because all the forces meet precisely at that center of gravity, they can only push or pull the object in a straight line. Concurrent forces generate zero rotational moment. They cannot cause an object to spin. There are two other orderly states. Collinear forces share the same line. Parallel forces run alongside each other. If a system meets none of these criteria, it is non-concurrent, non-parallel. This is the most complex state, where scattered forces induce both straight-line translation and rotational spinning. Correctly classifying your force system into one of these specific geometric categories is mandatory. The classification dictates exactly which mathematical formulas you are permitted to use to solve the problem. This 2D grid shows a single diagonal vector and how we apply vector resolution. By using basic trigonometry, we can break any diagonal force into two orthogonal components acting straight along the x and y axes, f cosine theta and f sine theta. To maintain mathematical consistency across these components, we apply universal sign conventions. Forces pushing up or pushing to the right are positive. Forces pushing down or pushing to the left are negative. We can also run this process in reverse, known as composition. This is where we calculate one single resultant force that executes the exact same physical work as multiple scattered forces combined. For two concurrent vectors, P and Q, we use the parallelogram law of forces. By drawing parallel lines from each vector, we form a parallelogram, calculating the resultant as the diagonal cutting through the center. The geometry of this parallelogram gives us our primary resultant equation. R equals the square root of p squared plus q squared plus 2pq cosine theta. To find the precise angle of that resultant, we use the direction equation. Tangent alpha equals q sine theta divided by p plus q cosine theta. You can bypass the full equation at specific boundary conditions. If the angle between the forces is 0 degrees, the resultant is simply p plus q. If the angle is 180 degrees, they directly oppose each other, and the resultant is p minus q. If the angle is exactly 90 degrees, the cosine term drops to 0, leaving you with the standard Pythagorean theorem. Whether you calculate this analytically with equations or graphically by drawing polygons, finding the resultant is how engineers compress multiple chaotic data points into a single usable variable. When forces are non-concurrent, meaning their lines of action do not intersect, they generate leverage.
We call this rotational effect a moment. This diagram visualizes a moment-specific mathematical formula: force multiplied by the perpendicular distance from the line of action to the pivot point. Just like linear forces, moments require a strict sign convention. You must designate clockwise as either positive or negative and apply it flawlessly across the entire system to calculate balance. When dealing with multiple non-concurrent forces, we rely on Varignon's principle. It proves that the moment of a single resultant force about a point is exactly equal to the algebraic sum of the individual moments of all forces about that same point. Varignon's principle is absolutely non-negotiable in statics. It is the only mathematical method that allows you to calculate exactly where a resultant force is physically positioned in a non-concurrent system. We can isolate rotational force even further into a state called a couple. A couple occurs when two forces of equal magnitude run parallel but in opposite directions, separated by a defined distance. Looking at this diagram of two parallel arrows, we see the difference between a couple and a standard moment. A standard moment depends on a pivot point and causes both pushing and spinning. A couple generates pure rotation, independent of where the pivot is located. We use the couple concept to analyze an eccentric force. This happens when a load is applied off-center, putting unequal stress on a support column. To solve eccentric loads mathematically, engineers artificially resolve the off-center load into two distinct, manageable parts. This animation demonstrates how we model that off-center load. We replace it with a centered downward force for pure compression, combined with a couple to isolate the pure bending rotation. Resolving eccentric loads into a central force in a pure bending couple gives engineers the data they need to predict structural failures, utilizing basic arithmetic instead of relying on complex 3D software simulations. The ultimate goal of engineering mechanics is balancing these chaotic, straining forces against each other to achieve a state of perfect static equilibrium. To get here, we build a specific mathematical toolkit. We assume the body is rigid. We utilize transmissibility. We resolve concurrent vectors to find a resultant, and we calculate moments and couples for non-concurrent forces. Those tools culminate in the 3 unbreakable laws of equilibrium for a rigid body in a 2D plane. These 3 equations on the schematic grid confirm structural stability. First, the sum of all horizontal and vertical forces must equal exactly 0, guaranteeing the object will not translate in any direction. Finally, the algebraic sum of all moments must equal 0, guaranteeing the object will not rotate. Mastering the precise distinction between a force, a moment, and a couple, and knowing exactly when to deploy Varignon's principle, provides the mechanical engine you need to break down and solve any static equilibrium problem.